Hello guys, this presentation is related to the deliverable report in the context of InnoDC project. It is the third deliverable and it is about the mathematical framework for converter interactions modeling. And but what I'm going to talk about is the interactions and the stability analysis of MMC-based VSC-HVDC link. We are going to talk about a voltage source converter based HVDC link and how the control systems of the master and slave converters are going to interact with each other and how we can formulate these interactions. This is the contents. First, we are going to talk about the system. What is the parameters of the system? What is the configuration? Then we will cover the system mathematical modeling. We are not gonna talk about the details, but mostly about how we can drive state space equations of the control system, electrical circuit, cable, and how to combine them together. Once the model is achieved, the linear model is validated against the nonlinear model to make sure that our modeling approach is correct. And then once the linear model is obtained, the system analysis is conducted. Various system analysis, system stability with critical mode, sensitivity, and then system interactions, which is of highly interest. The system under investigation is an HVDC link with a master and a slave converter at both ends. The master converter is working on the DC voltage control mode, and the slave MMC is operating under active power control mode. These two MMCs are connected with an HVDC cable. MMC structure is presented here. As you can see, it's a typical MMC configuration. Submodules are half bridge. MMC is connected to a rather strong AC network. The short circuit ratio is 10, which means the AC network is really strong. And the AC networks impose the frequency and the AC voltage of the MMC. So MMC can control the power or the DC voltage. For the control system, we are adopting a control system based on energy-based control system, which is the energy between the arms and between the legs of the MMC is controlled with closed control loops. In order to model the system, we need to model the master converter, slave converter, and the HVDC cable. For the MMC, we need to drive state space equations for the electrical circuit, plus the state space equations of the control system. Master converter, as said, is operating under DC voltage control, and the slave MMC is working under active power control. Once all the state space equations of the system are derived, they are interconnected using similar inputs and outputs. And then after linearization, an overall linear model for the system is derived. This is the overall linear model of this system. There is master MMC, slave MMC, HVDC cable, and these blocks represents control system. At this part, we validated the linear model against the nonlinear model. For 10% step power change, we can see that the AC power of the MMC number 1, which is master MMC, the grid current, the Q-axis grid current, total energy control, and the DC voltage. Both of them, the linear and nonlinear model, have a good match. They are accurate enough for our study, actually. Once the model is derived, now we can conduct different analyses. First, we can find what is the critical modes of the system. By critical modes, I mean that which modes of the system have the lowest damping ratio. With the eigenvalues we have, we can derive the damping ratio of the system as it is indicated in this figure. These 10 eigenvalues from 1 to 10 has very low damping ratio, and all of them are related to the HVDC cable parameters. We found this based on the participation factor. So we have here eigenvalues and here participation factor. The red square indicate that these specific state variables has the highest impact on these eigenvalues. So we can attribute this eigenvalue to these state variables. So with this way we can find which state variables actually excite which critical modes. Therefore, for 10 critical modes which happens to have very high frequency, the cable parameters contribute a lot. So 10 high frequency modes related to HVDC cable parameters, this is found from participation factor analysis. And next, there are 2 conjugate modes here which are actually excited by the PI controller of the DC voltage control. And these 2 have a more or less low frequency, 375 radian per second. And these 2 eigenvalues are related to the state variables of the DC voltage PI controllers. So at this point of a study, we detected the system critical modes, 10 high frequency modes and 2 low frequency modes. Once we know that what parameters are of importance, we can conduct system sensitivity. So as we mentioned earlier, that cable parameters and the DC voltage PI controller contribute to the critical modes of the system. So we would, with the variation of the cable length and DC voltage PI controller coefficient, we can observe that the dominant eigenvalues of the system would change from for example, when the cable length is reduced from 200 to 20, the system becomes unstable. It means that for the shorter cable length, the system is prone to instability. The DC voltage and the total energy control loops, they show that when the cable length is decreasing, the system undergoes high transient. This is the same in the system sensitivity with regard to the DC voltage PI controller. When the gain of the PI controller is reducing from 1 to 0.1, the system becomes less stable. This one is also confirmed with the time domain analysis. Next step is to have a look at the system interactions. The border plot could be of interest. So the system has 10 inputs and 4 outputs. The inputs are selected based on the importance, and the outputs are mainly the control variables of the system. With the 10 inputs indicated here, we can find the body plot of every individual output. So in this figure, for example, the DC voltage, we can see that for low frequency, the DC voltage controller is highly dependent on its own reference, which is the DC voltage here. But when the frequency is increased, for the frequency equal to the critical mode, low voltage critical mode 375, we can see that the DC voltage control loop is no longer affected by the DC voltage reference. On the other hand, the reference for the total energy has high impact on the DC voltage control loops. So we can find an order here. For example, at this specific critical frequency, which inputs have larger impact on the output. So we can continue with the same analysis for the total energy of the MMC1, total energy of MMC2, and the power loop. The result can be represented at the critical frequency like this figure. We call it normalized input participation. For example, for the DC voltage, the highest participation of the input, which means that the input with the highest impact on the DC voltage, with the highest impact, I mean with the this input can cause the larger transient on the output. So at this specific frequency of the critical low frequency, we can rank the inputs, which one has the highest impact. For the other 3 outputs, we can do the same. Again, with the time domain analysis, we can validate the results we obtain from frequency domain analysis, and all the analyses are consistent. To complete the interaction studies, we need to conduct RGA analysis, relative gain array analysis. So relative gain array analysis is conducted on the 4 control loops. It actually indicates how the control loops are interacting with each other. For example, we have 4 control loop references. The whole system has 4 major control loops, therefore 4 control references. So if we conduct the RGA analysis between the reference of the DC voltage and, for example, the total energy of MMC1, we can find the interaction between these 2 control loops. So for the 4 output we have and the 4 references we have, we conduct RGA analysis, and we can see that at low frequencies, the 3 control loops, DC voltage, total energy 1, and total energy 2 related to the MMC2, are highly coupled with the references, and the mutual interaction between control loops are not significant. This means that the control system is designed properly for low frequency. However, for the frequency of 375, the control loops begin to heavily interact with each other. So as you can see here, for this critical frequency, the DC voltage control loops are not only interact with its own reference, but it starts interacting with other references of the system. This means the interactions between control loops are becoming more severe at this critical frequency. At some point, DC voltage control loop is coupled to the total energy control loop of MMC2, which means that the control system of MMC1 is heavily coupled with the total energy control of MMC2. And these two MMC are interacting through the HVDC cable. The same scenarios can be explained for the total energy of MMC1 and MMC2. An interesting point here is that the total energy of the MMCs are really important, and they can affect the dynamics of the DC voltage control loop and the total energy control loop of MMCs. Total energy control of MMC1 is interacting with its own reference, but at the same time, the reference of the other MMC, which is located far away from this MMC at the other side of the HVDC link, is also interacting with the total energy loop of MMC1. The power loop here, the power loop is kind of working independently from other control loop, because in the power control loop we have feed forward, which kind of remove the transients of the DC voltage on the power loop, and this so the power loop is not a major concern with regard to the interactions. The DC voltage, total energy 1 and total energy 2 for two MMCs are more critical. To quickly draw some conclusion, we discussed that HVDC link, after providing a mathematical modeling, nonlinear model, then we linearize it, interconnecting models, and achieved an overall model, a linear model, and study eigenvalues, and we found out that there are 12 critical modes, 10 with high frequency and 2 with low frequency. The high frequency modes are related to the cable parameters. 2 low frequency modes are related to the PI controller of DC voltage. And finally, with the interaction analysis, we can see that the total energy control loop of a slave MMC would have impact on the DC voltage control loop of master, and also the total energy control of the master MMC. The RG and the normalized participation factor both indicate that in the procedure of designing an MMC-based HVDC link, the total energy control of MMC is highly important. This is what differentiates MMC from the traditional two-level converters. So when we have MMC in your system, the total energy control loop is really important. I guess that's it, yes. Thanks for your attention.